Hello, and welcome to the video of me, Julia Surchuk, solving problem 1.60a from the textbook. The problem statement is, the diameter and surface emissivity of an electrically heated plate are D equals 300 millimeters and epsilon equals 0.80 respectively. Estimate the power needed to maintain a surface temperature of 200 degrees Celsius in a room for which the air and the walls are at 25 degrees Celsius. The coefficient characterizing heat transfer by natural convection depends on the surface temperature and, in units of watts per meter squared, Kelvin, may be approximated by an expression of the form H equals 0.80 times Ts minus T infinity to the power of 1/3. First, we will start with our givens for the electrically heated plate, whose diameter is 300 millimeters, or 0.3 meters, and an emissivity of 0.8. The temperature of the air and walls is 25 degrees Celsius, and the surface temperature of the electrically heated plate is 200 degrees Celsius. Lastly, the convective heat transfer coefficient is H given by the equation before. And what we are trying to solve for is power, or P elect, needed to maintain a surface temperature of 200 degrees Celsius. Now, before we start solving the problem, we need to state our assumptions. We are under steady state conditions, working with one-dimensional heat transfer with uniform H and uniform Ts. And lastly, for radiation, we have a small body and large enclosure. To start solving, we need to determine the modes of heat transfer occurring with the electrically heated plate. First, we will define our control volume, which is outlined in the green dashes. Now, in terms of heat transfer, we have the electricity generated, P elect, from the electric heater entering our system, as well as heat from convection and radiation leaving our system. Therefore, the sum of the heat from the convection and radiation should be equal to the electricity generated by the electric heater. But before we can do that, we need to solve for convection and radiation. We will start by solving for the area of the electrically heated plate with the formula A equals pi times d squared over 4. Then we will plug in our given values and get our area to equal 0.071 meters squared. Next, we will take the given formula for the convective heat transfer coefficient H and plug in our given values, and we will get H to equal 4.475 watts per meter squared Kelvin. Now we have the needed variables to solve for convective heat, so we will take our 1D convective heat formula, Q convection, which equals H times A times Ts minus T infinity. So we will plug in our givens and the solve for variables, which will give us Q convection to equal 55.60 watts. The last thing we need to solve for is the heat from radiation. Since we assumed small body, large enclosure, we have the formula Q radiation equals epsilon times sigma times A times Ts to the fourth minus T infinity to the fourth. We will then plug in the given and solve for variables, which will give us a value for Q radiation to be 135.96 watts. Finally, we can solve for the power generated by adding the heat from convection and radiation. And when we plug in those values, we get a final answer of 191.56 watts.